Hello, let's take a look at our first example problem from Chapter 2. So before I begin, I just want to show you the two additional resources I have pulled up. So first is over here, I have a copy of the scanned appendix from our texts that are posted on Canvas. We'll have to use the Steam tables for this problem. The other reference I have up is our lecture notes, so part 1, and that's just in case feel compelled that I need to look at a phase diagram to help me with any of the problems. All right, but without further ado, let's give it a try. Okay, and so problem 1, part A, B, and C are associated with identifying the phases, and we'll also get some experience looking up data in the Steam tables. Okay, so here we go. So let's start with part A. So use the steam tables to determine the phase of water, liquid or vapor, at the following conditions. 25 degrees C in 1 bar, 80 degrees C in 10 bar, and 120 degrees C and 50 bar. Okay. All right, so A, okay, let me call this part 1. So our temperature is 25 degrees C, okay, and our pressure is 1 bar. So I could picture myself either on a PT or a P versus V phase diagram where I have isotherms drawn. Okay, either would be fine. But what I'm going to need to identify for this problem is a reference point. Right, and so basically it's going to come down to is pick your favorite variable, either temperature or pressure. Okay, so when we go over the steam tables, right, my first thought is I think I'm going to be looking at the saturated steam tables. And so I believe those are compiled in increments of temperature. And so I'm probably going to be thinking in terms of temperature. But what I want to find out is at 25 degrees C, what's the saturation pressure? So 25 degrees C, at what pressure do I have vapor-liquid coexistence? Because then what I can look at is my actual pressure in comparison to saturation. Because if my actual pressure is greater than my saturation pressure, then I must be a liquid. Okay, at that same temperature, right? So I could think about a P versus T where I'm drawing an isotherm, right? So actually, let me just go over here so we can walk through it. All right, so if I go down to my PT phase diagram, right, I have this scenario. All right, so I know my temperature is 25 degrees C, right? So I could draw an isotherm, which is this vertical line. And so what I want to find is my reference point. At what pressure am I on my equilibrium line? Because then if my actual pressure is greater than that value at saturation, that means I'm up here, I'm a liquid. If it's less than that value, then I'm down here, I'm a vapor. Okay, and you could go through the same thought exercise, if you wanted to, if you had pressure fixed, right, and you find out what the corresponding saturation temperature is at that pressure, and then you could compare your actual temperature relative to that value at saturation. Okay, either can allow you to achieve that same answer. Okay, so let's go over to the steam tables and let's see what we have and what might be easier to navigate. All right, so start at the beginning just so you can see what we have. Okay, so in terms of the steam tables, all right, the first table is for saturated steam. So this would correspond to data on that equilibrium line. Okay, and this is collected in increments of temperature, okay, where that temperature is in units of degrees C. Okay, so it's 25 degrees C on here. Well, 25 degrees C isn't exactly on here. All right, I have 24 and 26. All right, so in theory, I would need to interpolate between these 2 points. Okay, but let me just write a range because I don't believe that we're going to have to interpolate here, that we can figure it out. Okay, so let me write that at 24 degrees C, PSAT is equal to 0.02986, and we'll get the units in a second. 0.02986. And at 26 degrees C, PSAT is equal to 0.03364. Okay, the units I believe should be bar. All right, the units are bar. Okay, so at 25 degrees C, all right, I know my pressure is going to be between these two values. Okay, in either case, that's going to be less than my actual pressure of 1 bar. All right, so the answer is liquid. All right, and so this is a nice problem because this is atmospheric temperature and pressure, right? I know at 25 degrees C in 1 bar at atmospheric temperature and pressure, right, I have a liquid, right? And in fact, at 1 bar, so atmospheric pressure, I know that water boils at 100 degrees C, right? So I know that this, should correspond to liquid, right? By, going through our thought exercise and actually looking up data in the steam tables, right? We confirm that in fact it is a liquid, okay? All right, so now let's look at 2. So for 2, we have a temperature of 80 degrees C and a pressure of 10 bars. All right, and if I had to make a guess, well, I know that at 1 bar, Tsat's 100 degrees C. So now my temperature is lower and my pressure is higher, right? So my guess would be I have a liquid. Okay, but let's look it up and confirm. So if I go back to my steam tables, so let's see, is 80 degrees C on here? Yep, 80 degrees C is on here. So 80 degrees C is equal to 0.47 bars. Okay, and that's at 80 degrees C. So since my pressure is greater than the corresponding saturation pressure at that temperature, right, we must have a liquid. Okay. All right, and at 100 degrees C, Psat's 1 bar, right? At 1 bar, water boils at 100 degrees C. All right, so that's another one that you might, in theory, be able to answer without actually looking up any data in the steam tables. Now C. So now we're at 120 degrees C. And our pressure is 50 bars. All right, I would guess again liquid. We're again, 1 bar Tsat's 100 degrees C. Well, let's look it up and see what we have. So 100 degrees C makes it. So at 100 degrees C, Psat was equal to 1.987 bars. So since my pressure is greater than Psat at 120 degrees C, all right, we must have a liquid. All right, cool. So that's the first part involving steam. So let's add a new page and let's look at part 2. Or B, I guess it is. So B. So now we're told the vapor pressure of bromobenzene at 40 degrees C is 10 millimeters of mercury. Determine the phase of bromobenzene at 40 degrees C and 1 atm. Okay, so here I don't necessarily need to, look anything up. Right? Key is that 1 atm, is equal to 760 millimeters of mercury. Okay. So in terms of pressure conversion, typically I remember values at 1 atm. Right? So 1 atm is 760 millimeters of mercury. If you're unsure, at the top of the appendix, right, we have our conversion here. But so at 40 degrees C, my saturation pressure, so vapor pressure, the saturation pressure of bromobenzene, when it says vapor pressure, it's corresponding to saturation pressure, right, of bromobenzene at two-phase equilibria. So at 40 degrees C, Psat is 10 millimeters of mercury. So now my actual pressure is 760 millimeters of mercury. So since P is greater than Psat at that same T, right, again, we must have a liquid. Okay. So B, I don't necessarily need to do anything. It's just, rather than scroll down and write it out, right, I can, find that I have a liquid. All right, now C. So now the normal boiling point of fluorobenzene is 84.7 degrees C. What is the phase of fluorobenzene at 25 degrees C and 1 atm? Okay, so again, I don't necessarily need to do much. Okay, it's just picking up some jargon. So the jargon is, we're told the normal boiling point. Okay, so normal boiling point is going to correspond to the vapor pressure, right? Or, since we've got temperature, you can think of it, pure fluorine boils at a pressure of 1 atm. All right, so normal boiling point is going to correspond to a property at 1 atm. Okay, so the normal boiling point of fluorobenzene is 84.7 degrees C. So at 1 atm at atmospheric pressure, fluorobenzene boils at 84.7 degrees C. Okay, so that's equivalent to saying at 1 atm Tsat, and my saturation temperature is 84.7 degrees C. So now if I'm at the same pressure, right, but my temperature is lower, right, so now I have T is less than Tsat. So now I'm comparing temperatures and thinking in terms of temperatures. So rather than thinking in terms of this vertical, right, now I'm thinking in terms of this horizontal, this isobar. Okay, so now if my temperature is less than the value at saturation, right, the reference point we're given is at a given pressure, we're given the value of Tsat. So now Tsat is less than, or T is less than Tsat, right? So again, that's going to put us down in the liquid. Okay. Cool, right? And so it's essentially the opposite. Okay, but for C, we find we have a liquid as well. So in problem 1, in this case, they're all liquid. Okay, but the thought exercise, boils down to thinking in terms of a PT diagram. And so if you didn't have this example here, right, you could just as well sketch, your curve, right? This is an exponential curve, liquid up top, vapor on the bottom, and you could go through your thought exercises then of identifying phases. Hope that helps.